short here. We'll go through these just one at a time. If there's one you want to see, just say yes. Otherwise, we'll just move on to the next one. So we'll just start off with number 1. Okay, everybody's with number 1. Just got to make sure all the elements are balanced and the total charge is balanced on both sides. Number 2. Okay, good. Number 3. All right, we'll be out here in 5 minutes. Number 4. Okay. Yes. Okay. Yeah, don't be afraid to speak up. That's all right. That's what we're here for. So number 4 says, which is the reduction half reaction in the following reaction? Okay, so let me go ahead and write out the entire reaction here. We've got zinc solid plus 2H plus, and that's going to go to Zn2 plus H2 gas. So if we write out our half reactions, we're going to have our Zn going to Zn2 plus, and we're going to have 2H plus going to H2 gas. So now we've got to balance our half reactions, and we go through all of the steps. The only thing we have to really do here is just add some electrons because everything else is balanced. So I've got to add electrons here on that side to balance out the charge, and I need to add 2 electrons over here to balance out that charge. And so we're looking for the reduction half reaction. Reduction is gain of electrons, and so that gain of electrons would be those 2 electrons as a reactant there. And so the 2H plus going to H2 is what would be our reduction half reaction there, and then with the 2 electrons added in as well. Okay, questions on that one at all? All right, so that was number 4. Number 5. Yes. Okay, I got a lot of questions on this one in my office hours. Not a whole lot to look at on this one, but we've got an E. Oops, 0 goes up there. So you got an E0 reduction. So reduction potential for A is equal to 1.0 volts. We've got a reduction potential for B of negative 0.50 volts. Okay, so when we put these 2 things together, which of these 2 is going to be reduced, A or B? Okay, A is going to be reduced because it has a higher reduction potential. Okay, the higher the reduction potential, the more likely it is to be reduced. You can think of it that way. So if it has a higher one, it will be reduced in those in a reaction between the 2. So that means that this will be oxidized. Now for the agents, you got to go back. Remember, reduced and oxidized is what happens to those 2 things. A is reduced, B is oxidized. Now as far as an agent, when we talk about an agent, that's what it does to something else. So if we look at A, it's reduced. That means it gained 2 electrons. Well, where did those 2 electrons come from? They came from B. It made B get oxidized, and so A would be the oxidizing agent. And since this is oxidized, it made A take 2 electrons. And so B would be the reducing agent. Not reduced, reducing, sorry. Okay, reducing agent. So that's why the answer there is B. That is the reducing agent. Okay, the other thing to remember, if you were given like an entire chemical reaction, your agents are always in the reactants. Okay, they're always in the reactants because that's what you're reacting. The products are just what are made. Okay, questions at all on that one? Okay. Let's see, number 6. Yeah. Okay. Why didn't I write down all my? I didn't write down all my equations on that one. So for number 6, I think I had it on a different a different sheet. So the equilibrium constant K for a process at 298 K is 5.5 times 10 to the minus 6. What is the standard cell voltage if this is a 2-electron process? Okay, so we know as we've got E cell, it's going to be equal to 0.0592 over n log of K. Okay, we're told it's a 2-electron process, and we're given the value of K, so we just need to plug all that in. Over 2 log of K, so that's 5.5 times 10 to the minus 6, and when you plug all of that in, you get a value of negative 0.16 volts. Look at 6. Here we go. Okay, any questions on that? So one thing you might want to do is, if you remember on some slides, and the slide came out of your book, there was a triangle that had equations that related G and K, G and E, E and K. Okay, so all three of those quantities are linked together through equations. You want to make sure you've got all those on your card. Any questions on 6? Okay, how about number 7? Yeah? Okay. So for 7 it says, what is the purpose of a salt bridge in an electrochemical cell? So the correct answer there is E. Okay, the salt bridge keeps charges neutral in the solution by replacing charges that are removed and countering charges that are added. Okay, so if you remember, we've got oxidation processes and reduction processes happening, in each half cell. Where oxidation is taking place, you have electrons leaving atoms in the electrode, and it's spitting off cations into the solution. Well, when we made the solution, we had a neutral salt, and we put that into the water, and we had an equal number of positive and negative charge, and that's the way nature has to have it. So when you start pumping positive charge into that solution because there's positive ions coming off of the electrode from the oxidation process, the salt bridge has to counter that by dumping in negative ions. Okay, so if you had something like potassium nitrate, and you had like zinc 2+ coming off of an electrode, it's dumping nitrates into that solution to counter those extra pluses to make sure that that solution stays neutral. On the other side, you've got reduction taking place. So now you've got positive charge being removed from the solution. You might have something like a copper ion plating from Cu2+ to copper metal. Well, now you're removing positive charge out of that solution. Nature doesn't like that anymore. And so the salt bridge has to pump in positive ions in there. In this case, potassium ions would be going in to replace the copper to make sure that that charge stays neutral. Okay. It also looks at a continuation of flow. If you think about our reactions here, we always had the anode over here, we had the cathode over here. It doesn't have to happen that way. It just seemed to be the way our drawings went. So our electrons came up the anode, through the external circuit, down into the cathode, and there the electrons stopped, but the flow of negative charge kept going because the salt bridge negative charge is going to go this way. So your flow of negative charge goes like this, in a big loop, around the external circuit and then through the salt bridge. Okay, so it just makes a circuit of negative charge. Yeah? So D says that it completes the circuit by allowing electrons to flow back where they started. But the electrons don't flow. The electrons go through the external circuit and then they stop because they're involved in the reduction process. Okay, the negative charge in the salt bridge is from the ion in the salt bridge. Okay, everybody good with that? I had a lot of questions on that one this week too. Let's see. How about 8? Yeah, okay. So for number 8, we've got a redox reaction there. Okay, so we've got 2 Ag plus cadmium going to 2Ag plus CD 2 plus. Okay? So, when we write out our cell notation, we want to make sure that our anode is always on the left. So we start with our anode. So we've got to find our oxidation process. Which of these two things is being oxidized, the cadmium or the silver? It's the cadmium. We see the cadmium is going from CD with a 0 to CD 2 plus. And so it had to lose 2 electrons in this process. So that's my oxidation, which means that that is my anode. And so we're going to list that one first. And we list it in the order that we see it in the reaction. So we can go cadmium there, phase boundary, cadmium 2 plus. Then we've got our salt bridge there. Okay, and then we're going to write the silvers there. And we don't have to include, we don't include the coefficients for our cell notation. And so we're going to write it left to right here. So Ag plus appears first. Phase boundary. And then Ag there. Okay, the other way, if we were going back the other direction, this guy here is always going to be a reactant. This here is always going to be a product. This is always going to be a reactant. This is always going to be a product. Making sense for everybody? Any questions on that? All right. Let's see. Number 9. I don't know why I wrote it. Nobody has a question on it. Everybody good with that? Okay. Does everybody understand the difference between A and D on that one? No? Okay. So you should have said, yeah, I've got questions. Don't be afraid. Okay. So, why does an electrochemical cell have an oxidation half reaction and a reduction half reaction? A and D look kind of the same, but the order becomes very important because you've got to remember what's losing electrons. Remember oil rig. Okay, so the oxidation process is losing electrons. Oxidation is loss, or Leo goes grr, loss of electrons is oxidation. So, something is losing the electrons and then something is gaining the electrons. So the electrons from the oxidation, okay, so the oxidation is giving up the electrons is what that says. And then it's used in the reduction. The reduction gains those electrons, so it picks them up. Okay, the reason we can't do D is because we don't use electrons in the oxidation. The oxidation is losing the electrons. The electrons are a product of the oxidation process, whereas they're a reactant of the reduction process. Does that help clear up those two answers a little bit? Didn't really need to write that one in. Number 10. Yeah. Okay. So 10's kind of a weird one. I think if I were going to break out number 10 into the two reactions, because we're looking for the cathode half reaction. So let's just write out our two half reactions. And I would normally have written them out unbalanced, even though they give us a complete balanced reaction. It's a lot easier to see what's going on in the unbalanced half reaction, and then you can rebalance it later. So let's take a look. So we always want to look at the elements other than hydrogen or oxygen that we've got in there. So we've got Mn2 plus, and that's being turned into MnO4 minus over there in the products. And then we've got SN4 plus, and that's getting turned into SN2 plus. Okay, now we can look at these a little bit individually. We can look at oxidation states just to see what's being oxidized and what's being reduced without having to go through and balance them if we want. If we look at the manganese here, it has a +2 oxidation state because it's a manganese 2 plus. Over here, if we go through our rules, we see that oxygen has a -2. There's 4 of them for a -8. The sum has to equal -1, So that manganese has to be a +7. So the manganese went from a 2 plus to a 7 plus, or a +2 to a +7. So is that oxidation or reduction? It's oxidation. It had to lose 5 electrons. Okay, the tin went from 4 plus to 2 plus. So it went down, so that is what process? That's reduction. Now it didn't ask me what was reduction or what was oxidation. It asked me for the cathode. And the cathode always goes with which one? Reduction. Okay, so this is my cathode. And so this is my, that's my reduction half reaction, or the half reaction at the cathode. And all we have to do is just balance that one out, and we need 2 electrons there to make that one balance. Okay, so I really simplified that one by just throwing out the waters, throwing out the H pluses, just getting rid of all that stuff that we use to balance it. Because all we wanted to know is just what's oxidation and what's reduction. Okay, and the easiest way to look at that is just look at those elements that are not oxygen and hydrogen. All right. Questions on that one at all? Okay, number 11. Yeah? Okay. So it wants to know what is the balanced redox reaction for the reaction of sulfate with chromium 2 plus to give H2S and Cr3 plus. I think I'm going to go to the next page for that. Let's go with number 11 there. All right, so we're given our reactants and products. That's nice. So we've got SO4, 2 minus, and its half reaction is really going to go to H2S. Then our other half reaction is a chromium 2 plus, giving us chromium 3 plus. Okay, so that's always the first step in balancing. Write out your reactions as half reactions. And so now let's just go through our steps of balancing. Balance everything that's not hydrogen or oxygen. Well, I got 1 sulfur, we're good. 1 chromium, we're good. We don't have to do anything there. Now we want to balance our oxygens with water. I've got 4 oxygens here, so I need to add 4 waters there. Okay. I don't have any oxygens in the bottom one, so I don't have to worry about it. Okay, now I need to balance hydrogens with H pluses. This is the tricky part on this top one, because a lot of people jump right to here and say, oh, I have 8 hydrogens. You got those little 2 hydrogens in that H2S. A lot of people miss that. I've got 10 hydrogens here and none over here, so I've got to add 10 H pluses to this side. Okay, and I don't have any H's in the bottom one, so I don't have to worry about that. So now we want to balance the charges with electrons. I've got a total of 8 pluses over here. I don't have any over here, so I'm going to add 8 electrons to that side. I need to add 1 electron on this side to balance that out. Okay, so now I want to add those 2 together in such a way that my electrons cancel. So I just need to multiply this bottom one by 8, and that will cancel out my electrons. So now when we add everything up, the electrons cancel out, and I'm left with 10 H plus SO4 2 minus plus 8 Cr2 plus goes to 8 Cr3 plus H2S plus 4 H2O. Hopefully that's an answer. That should be D. Is that the right answer? Okay, good. Whew. I always worry when I work one of those out and I get it wrong. Any questions on that? How many of you missed the H2S on that? Yeah, it caught me once. I don't mean like once in my life, I mean like this morning. Because I was looking at it, it's like, oh, something's not right. And I was like, oh, there it is. It's that H2S. Dang, that's sneaky. All right. Number 12. Yep. All right. So, an electrochemical reaction involves the transfer of two electrons and has an equilibrium constant at 298 K of 1.68 times 10 to the fourth. What is the E0 for this reaction? So, very similar to the reaction that we did, or the problem we did just a little bit ago. We're going to use this equation here. E0 is equal to 0.0592 over n log of K. We're told it's a 2-electron process, and so that's going to be equal to 0.0592 over 2 log of 1.68 times 10 to the fourth. This is one of those times you got to be very careful about your finger. You get a lot of button push memory and you accidentally hit 10 to the minus 4. I did that this morning too. But I caught it before I did the calculation. It was just like minus. No, this is not a minus. This is a positive exponent. Okay, so when you just calculate that one out, you get 0.125 volts. Questions on that? One thing I've seen a couple people do is confuse this number and the correct log. Okay, remember there's a different formula if you use a natural log. It uses a different number up here. It's fine if you use it. But you can't mix the number and the type of log. If you're going to use a common log, log, then you got to use this number. If you use the natural log, ln, then you got to use like 0.0257 or something like that. Okay, they'll both work just fine. Okay, but you can't mix the numbers and the logs. You got to make sure you do it right. Let's see, number 13. Yep. So we got a galvanic cell, cadmium and silver under non-standard conditions. Has a potential of 0.986 volts. What is the free energy change for this reaction? Okay, so again, let's kind of write down what we've got here. We've got cadmium, going to cadmium 2 plus, and silver plus and silver. Okay, so our two half reactions are going to be cadmium going to cadmium 2 plus, silver plus, going to silver. Remember, reactant, product, reactant, product. Okay, we read each of those half reactions left to right. Okay, so we want to balance this, so we're going to need to have 2 electrons here. Got to have 1 electron here. Want to be able to add those up and get the electrons to cancel, so I'm going to have to multiply this by 2. So when I do that, my electrons will cancel out, and I'll get CD plus 2Ag plus goes to 2Ag plus CD 2 plus. Now what this told me is that my N value is equal to 2. Okay, and that's important. Got to know that N value for this calculation. The equation that we're going to use is delta G is equal to N F E cell. Sorry? Yes, sorry. Thanks. That's a negative. All right, so we're given E cell. And again, so the other question that I got today is what's the difference if it's delta G0 and E0? Well, that just means it's under standard conditions. Exact same equation, just either under standard conditions or it's not. And it just takes the 0 away. So we can write that either way. So let's go ahead and write our delta G here. So that's going to equal negative 2 for my N times my Faraday's constant, 96,485, times 0.986, the volts that was measured. And when you calculate that all out, you get a delta G of negative 190,268 joules. And when you convert that into kilojoules, you get negative 190 kilojoules. Any questions on that? Yep.
Can you go over how you determined that N was 2?
Because that's the number of electrons I needed here to cancel. Okay. It's always that lowest common multiple that you need to get to cancel out those electrons when you have the half reactions. Number 14. Yeah, I knew that one was coming. Concentration cells are weird. They take a while to get used to, but once you get used to them, they're really cool. All right, so again, let's write out our cell notation here that was given. It's not a very good cobalt there. Okay, and we're going to do products, reactants, products, I went the wrong way. Reactants, products, reactants, products. Okay, that's better. Okay, so I'm going to have CO plus my other reactant, CO2 plus, and that's the 0.187 molar, going to the other product, CO2 plus 0.012 molar, plus regular cobalt. Okay, it's important to know which one is going where, because it's going to affect your Q that you put into your Nernst equation. Okay, so we can write out that we have E cell is equal to E0 cell minus 0.0592 over N log of Q. Okay, what is my N going to be here? You can kind of see just by, it's 2. Okay, because I'm going from a 2 plus to a 0 charge in both cases. So that's going to be 2 electrons for N. All right, what's my E0 cell? It's 0 because I've got the same 2 metals. So remember, your E0 says if you were under standard conditions, so if the concentrations were exactly 1 molar, what would be the voltage? Well, if I've got the same metals at the same concentration, there's no reason for the electrons to go one way or the other. So it's going to be a 0 voltage there. So all of the voltage here comes as a result of the difference in concentration. So let's write out our equation here with everything we know. So our E cell is going to be 0 minus 0.0592 over 2 log. Now my Q value here, it's the same old Q, the same way we've been writing Q all semester. It's products over reactants. So my product is the 0.012 concentration over my reactant concentration, 0.187. How come I don't include those 2 COs out there? Because they're solids, they're metals, and we don't include solids in Q calculations. Okay, when I throw all of that together, I get a voltage of 0.0353 volts. Yeah?
Will the concentration on products always be less?
Yes. Yeah, the question is, will the concentration in the products always be less? Yeah, if they're writing it as a spontaneous equation, it will be, yeah. Now, it's possible they could swap that up and expect the negative voltage out. So, all right. Turn a couple of pages here. Okay, number 15. Okay, now 15, oh, it says E, okay. So number 15 is E. Okay, it does not involve rearrangement of atoms or the breaking and forming of chemical bonds. Those are chemical reactions that do that. Nuclear reactions focus only on the nucleus of the atom. Okay, and they are accompanied by the absorption of tremendous amounts of energy if it's a fusion process, followed, of course, by then the enormous release of energy. And then your fission also releases large amounts of energy. And then the conversion of one element or isotope into another, we see that happen as well through transmutation through our various emissions there. Okay, so that's why A and B are correct and why C is not correct. How about number 16? Everybody go 16? You guys knocked those out of the park today, so. How about 17? Yep. Okay, for the following neutron-induced fission reaction, filling the missing daughter product. Okay, all the daughter product is just, that's what comes out of the mother product, I guess you could say that. It's just called the daughter product. All right, so 17, we've got, you can't forget to count this neutron that's being added in here. When you're adding up all your totals. All right, so let's just add up the bottom first. Okay, I've got a total of 92 protons in the reactants. Over here I've got 38 and 0. So what do I have to add to 38 to get to 92? 54. Okay, so I know I've got 54 protons. Well, 54 protons is xenon. So I already know the element. That knocks out 3 of the options on the question there. And then I've got to make sure everything adds up over here. I've got a total of 236 here because I got the 235 from the uranium and then the 1 from the neutron. So I got a total of 236 there. I've got 80 and 3 from the 3 neutrons here. So that's 83. And so I've got to get that to add to 236. And that's going to be 153. So I've got xenon 153 there. And so that's going to be choice B. Any questions on that one? How many of you forgot to add in the proton at the start in the reactant? Yeah, it's common. Also common to forget that there's 3 neutrons in that product as well. Okay, got to be careful of those. Let's see, number 18. Yeah? Was that a yeah? Okay. I never know if people are just yawning or snoring or saying yes. Okay, it's number 18. We're looking for the alpha decay of uranium-238. Okay, well, if we look at the reactants, those are all uranium-238, so we can't use that. But an alpha decay means it's going to produce an alpha particle. An alpha particle is that, or it's that. Remember, an alpha particle is a helium nucleus. And so the only one that has that as one of the products is D. And so that's why D is the correct answer. It produces that helium nucleus, that alpha particle. Okay, those two things are the same. I think in this problem they didn't write it with an alpha because that kind of gives the problem. So they just wanted to see if you could recognize that alpha particle with just the 4 and the 2 there. Okay, questions on that? Okay, how about number 19? So number 19 is just kind of just a factoid that just came out in class. It comes from the band of stability. You might remember me saying that. Remember you had like that yellow cloud of all the radioactive isotopes, then you had that green band of stability. And as soon as you got above 83 protons, there was no more green band. There are no more stable isotopes there. That is not something I would expect you to memorize for the exam. Okay, that's just a little factoid kind of out there. So don't worry about that one. I also mentioned don't worry about number 20, because that also uses the band of stability, and it's trying to use that in any kind of quantitative sense is just insane, unless you got a really big one, and we don't. So don't worry about 20 either. All right. Flying dudes. 21. Good. 22. Yeah, okay, so again, just knowing terms. So alkanes are considered to be saturated hydrocarbons. And what that means is that they have as many hydrogens as they can possibly hold. You've got single bonds only between the carbon atoms, and that means that all the rest of the bonds around those carbon atoms are going to be hydrogen atoms. So that's why we call those saturated. Alkenes and alkynes that they list for A and C, those are both types of unsaturated hydrocarbons. So they have fewer hydrogens than they could possibly hold because they've used some of their bonding electrons to form either a double or a triple bond. And so once those are used to form the multiple bonds, they can't be used to bond with hydrogen anymore. So they have fewer hydrogens than a saturated hydrocarbon. Let's see, 23. That was a quicker question today. That's just memorization with the little formula there. 24. Yeah, I don't even know why I asked that one. I got asked that probably more than any other question today. So there's a couple of different ways that you could solve number 24. One is to notice that it specifies that what you're looking for is an alkane. Okay, so remember, we have that relationship between carbon atoms and hydrogen atoms in an alkane. So we have C to the Cn, H2n plus 2. So you want to add all of those up to see if any of them don't match that. Let's just look at the different ones here and see what they do. See if they match up. So A, we've got 4 carbons, and then we've got 3, 2, 2, and 3 hydrogens. Well, that adds up to 10, and that is Cn H2n plus 2. B, we have 3 carbons, and we have 3, 2, and 3 hydrogens. That's 8, and that is also fitting the formula Cn H2n plus 2. For C, that one's a little bit strange. Let me write C out a little bit differently here. That might help, because I know you're not used to seeing that condensed formula. So if we write it in the structural formula, I think an angel just got his wings. Why does everybody laugh when I chuckle? My wife does that too. She goes, "You're such a little boy." All right, so that's what that one would look like. I should have put this one down a little bit farther. But you've got you got that CH3, a CH, a CH2, CH3 down here, CH2, CH3. If we count up our carbon atoms, we have 6. So we have C6, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens, and that also fits CnH2n plus 2. Well, by elimination, that makes it D, but let's take a look at Y here. So D has got a couple of problems here, and 2 different ways of identifying it. Let me draw it out first. So we've got that CH3, we've got a CH2, CH, and that's bonded to another CH2, which is bonded to a CH3. Okay, we've got 5 carbons here, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens. Well, that's not quite right. Okay, that should be C5H12 for the proper formula. Where's the culprit? The culprit is that carbon right there. How many bonds does that carbon have on it? It's got 5. How many is it allowed? 4. Okay, so that carbon is the problem. That's why that compound is not a proper formula for an alkane. Not proper formula for anything, actually. Is that one making sense? Okay. Let's see, 25. Okay, so 25 follows along just kind of what we were doing. So all non-cyclic means is that it does not come up around and form some kind of closed geometry. It's not a triangle or a square or a circle. It's a line. It's a non-cyclic. That's why we say that. Because as soon as you form that cycle, the counts of carbons and hydrogens changes. So that's why it has to be specified there. So it's just an alkane with 7 carbon atoms. So if we've got C7, and we know it's got to be CnH2n plus 2, well, that's 14 plus 2, that's 16. So C7H16 has to be my formula, and that would be C. Okay, how about 26? Okay. So for 26, this idea about optical isomerism. Okay, for something to be optically active, that's another way of saying it has optical isomerism, it's optically active, is it has to have 4 different substituents, 4 different legs coming off of one of the carbon atoms on that compound. So let's look at the correct answer, because I don't want to draw out all the wrong answers, because that'll take me forever, and we'll be here until the test tomorrow, and then you won't get any study time. Because you'd have to try to sleep in those seats, and I know they're comfortable to sit in, but probably not very comfortable to sleep in. Although, I don't know, I've seen some people snooze a pretty good 50 minutes in some of my classes. Stop that. All right. So B is the right answer here. And the carbon that is optically active is this last one right here. Okay, so let's take a look at what's on it. Okay, it's got a hydrogen atom, it's got a chlorine atom, it's got a bromine atom, and then for this we need to look at the entire leg, not just the carbon atom attached to it. That would have been enough. But you want to look at everything that's attached to it. Remember that example that we saw in class on the slides the other day, where it had all carbon atoms attached to it. Well, actually, it had 3 carbon atoms and 1 hydrogen. And if you only look to the next atom, you'd say, well, there's 3 carbon atoms on there, it's not optically active. But it was optically active because it had a CH3 group as a leg, it had a C2H5 group as a leg, and a C3H7 group as a leg. And so you've got to look at that whole leg that's coming off of that chiral carbon, that optically active carbon. Okay, so that's why that one's correct. Any questions on that? Any questions? Yeah. Which one? Yeah, let me get you right out. Any last questions on that? All right, so it didn't take very long, so hopefully you guys are feeling pretty confident on the material. Best of luck tomorrow on the exam. I'll be in my office off and on if you need some help.